All right, folks, I'm going to jump right into these problems. I will say beforehand that the second problem is probably the more important problem to think about in this set. And if I were to place any bets, I would say that that setup that you'll see in the second problem will show up on the AP exam in the free response section. Anyway, here we go. So 2 second law rotation problems. Lots of data in this first one for the calculations. We have a ladder that's 10 meters long, and has a mass of 23 kilograms. It's on the ground. A painter lifts one end with a vertical force of 245 newtons. This gives the ladder an instantaneous angular acceleration of 1.80 radians per second squared, while the other end remains on the ground. Calculate the ladder's rotational inertia. So we are looking for an expression for iota for this ladder. I'm going to again start off with the force diagram as I would for anything involving multiple forces on an object. Now, we have to be kind of careful about this force diagram because it identifies the axis. I'm going to identify the axis as this location. And we have to put a location for each force. We're not going to put multiple locations. So the easy one is going to be right in the middle. I want to put the force of gravity on the ladder itself. And then the other easy one is on the right edge. I'm going to put this vertical force F, and that's 245 newtons. The thing that might be a little bit of a gray area is what do I do about a normal force? Because the ladder's on the ground, the whole ladder's on the ground. And what I'm going to do is we're going to consider a moment that is a fraction of a second after the right end of the ladder gets lifted off the ground, and we're going to put a normal force there. That ends up not being at all consequential because that force is going to be on the axis, but you really couldn't put that anywhere else because as soon as that ladder starts to be lifted, it's only one point on the ladder that's on the ground. All right. These 3 forces divide up the ladder nicely. We have one 5-meter segment here and one 5-meter segment here. So we're going to calculate the rotational inertia of this ladder using those 2 forces and a given angular acceleration. So relatively speaking, this is kind of easy. The net torque, I'm going to assign the positive direction as counterclockwise, as you would usually do. And we'll say the torque due to that force F is positive, but the torque due to the weight of the ladder is negative. And that's going to equal iota times alpha. And that's kind of it. As long as I can calculate the torques correctly, I'm going to be able to plug in the other values and be done with it. So this torque due to force F, that force is located the full 10 meters away from the axis, right? Because it's the right end that gets pulled or pushed like that. So 10 meters times 245 newtons. All right, so that's the upward torque. The downward torque is due to the force of gravity. Force of gravity is acting at the center of gravity of the ladder, and that's 5 meters away from the axis. And then the mass of the ladder is 23 kilograms, and I'm going to use 10 for G. So those are the 2 torques, and that's equal to rotational inertia times angular acceleration, so 1.80 radians per second squared. So, the torque side of things is the tricky side. You want to make sure you understand where these distances come from and where this force mass times little g comes from. But if we're solving for rotational inertia, that means we don't have to worry about the expression for it. We're just solving for the variable. Anyway, if you plug in all these numbers for the torques, divide by 1.80, you get a rotational inertia of 722 kilogram meters squared. Now, I will say that a 10-meter ladder is a very long ladder. That's something that a fire department would own, but not many individuals would own a ladder that long. All right, next one. Here we go. A pulley of radius r has a string over it that holds a block of mass little m, as shown, using iota equals 1/2 mr squared for a pulley of mass m. Derive an expression for the acceleration of the block. Pretty important to note that we're talking about the acceleration of the block, and so we are looking for an expression for the linear acceleration of that block. We're going to start with force diagrams, and then we're going to go from there, and this one gets a little complicated. Before I start anything, I want to again take note here. In this situation, the pulley has mass, and that creates enough inertia that it needs to enter into our system. When we did labs with pulleys and we analyzed pulley systems in Unit 2, we ignored the pulley altogether, and it never entered into any conversation about Newton's second law. And that's just because the mass of the pulleys that we use in physics are so small that their rotational inertia is negligible. And so these situations, if you see a pulley and you see it's like rotational inertia, you have to factor that in, and this is really going to be a rotation question. This pulley has enough rotational inertia that it's going to interfere with the acceleration of the block. So I'm going to start with the block itself down here, a diagram of the forces on block M would be the force of gravity, mg, and then the tension. Now I'm going to use Ft for tension. You can use T. I did it in another problem in this section, so that's fine. That's the forces acting on the block. The pulley has its own set of forces. So I'm going to draw the pulley as a circle, and I'm going to put a dot at the center because that's going to be the axis for the pulley. Now, the only maybe obvious force here is going to be on the right-hand side, the tension force. The other forces that have to exist are gravity. There has to be a force of gravity. I'm going to use capital mg for gravity. And then because the pulley itself, the center of mass of the pulley is not moving, right? It's like not falling with the block. There has to be some sort of support force. So you can call that whatever you want. You can call it a normal force. I'm just going to call it F because there has to be a force that is acting on that pulley. You wouldn't want to do this on an AP exam, but I am also on this diagram going to draw a line that represents the radius of the pulley. The reason you wouldn't want to do this on the AP exam is because when you draw this diagram, it can only contain forces. It can't contain components of forces, and it can't contain any other measurements whatsoever. So I'm putting it there so that you realize that that tension is happening at a distance away from the axis that is equal to the radius of the pulley. And so now we need to derive an acceleration expression for the block. So I am going to continue with the block down here. And the thing I want to do first is assign like a positive direction. Now the block is going to fall, and so the acceleration, the linear acceleration of the block is going to be that way. The pulley, because of the string, is going to rotate, and so the angular acceleration is going to be that way. It's going to be clockwise. I'm going to make both of those directions positive. Now, it's not going to be difficult to make the decision in the AP exam because you're usually told, but you need to make sure that those directions are compatible. The direction that the block accelerates has to match the direction that the pulley accelerates. Otherwise, you'll have a sign error, and that might throw you off. Okay, so now that we have that, the block is going to have a net force on it, and that's equal to its mass times its acceleration. Now, I'm starting here because this is where the acceleration is of the block, and so I want to start there. The net force is going to be mg is the positive force minus ft, and that's equal to m times a. Now, I know I can't solve this equation. In other words, if I solved this for a, I would be left with tension in there, and that's not one of the given quantities here. So I'm going to just leave that here for now. And I am limited by that. I have to now consider the pulley. The pulley, that tension force delivers a net torque. So I'm going to start with net torque equals I alpha. And this is where this problem gets really difficult. The easy part is the net torque. The only force out of these three that can possibly produce a torque is tension. And since it acts at a distance that's equal to the radius, the net torque on this pulley is R times Ft. Now, before I put anything into this equation, I just want to remind you, iota equals 1/2 mr squared. And I'm going to have to combine these equations at some point in time. So I'm going to need linear acceleration in both of them. And linear acceleration is equal to r times angular acceleration. So I'm going to use that equation right now in this expression. So I perform essentially 3 substitutions in this equation. For net torque, it's r times Ft. For rotational inertia, it's 1/2 mr squared. And then finally for alpha, for angular acceleration, according to this equation, alpha is going to equal linear acceleration divided by r. That r is going to be a capital R, because the distance, and this is another confusing part, the distance at which the block essentially is from the pulley is equal to the radius. If you continue up the block, the string goes up to the pulley, and the string is always going to be a distance r away from the axis of the pulley. So the string is kind of like part of the pulley, but also holding onto the block. In other words, the linear acceleration of the outside edge of the pulley is equal to the linear acceleration of the block. The block is connected to the string, and the string is connected to the pulley. So that is what allows us to make that combination. And so once you do that, now it's just math, but that's like the really hard part. What I'm going to do is I'm going to solve this for, what am I going to solve this for? I'm going to solve this for tension, and then I'm going to substitute it in. So I would divide both sides by r, and if you do that, you'd notice that you'd have r squared in this denominator. If you look at everything else that's here, the 1/2 will remain, the big M will remain, and the linear acceleration will remain. In other words, these r's will all cancel. There's r squared here, divided by r, and then divided by another r. So this expression is going to be fed down there. And I'm going to put everything over here so I have room to work with it. So I'm going to take this equation and combine it with this equation. And what I'm left with is little m times g minus 1/2 big M times A is equal to little m times A. Now the mass of the pulley and the mass of the block are different, and so you have to use different variables for them. If I combine like terms and solve for acceleration, I would get the linear acceleration of the block is equal to mg, that's the weight of the block, over 1/2 big M plus little m. And this expression essentially represents the Newton's second law expression for linear motion. You have the net force on the system, which is the force of gravity, and then you have what amounts to the mass of the system, although it's really not truly the mass, but it takes into account the rotational inertia. I know this is a long video, but this second problem is very instructional for all of the ways you can work with Newton's second law in rotation. Thanks.